Okay, so well, good morning to everybody, and thanks a lot for joining to the second edition of DYNAeLAST Expert Talk. Good morning, Seti, how are you?
Fine, I'm fine. You?
Okay, so well, before starting the presentation, just a few words from the article related to this DYNAeLAST event. Well, just to remark that we want to DYNAeLAST to be a forum of exchange of information and to meet people that are interested in thermoplastic elastomers and elastomers in general and dynamic applications. And well, this year we have selected also the online version of the workshop. But well, we are not discarding that maybe next year we can also include some presential meetings in the DYNAeLAST editions. Well, it's more than 15 months since we celebrate the first edition of the DYNAeLAST. It was June 22, and during those last months, of course, we have not stopped our research activities in elastomers and dynamic applications, following our more traditional research activities related with conventional thermoset elastomers, and of course including a lot of activities and more activities related with thermoplastic elastomers related projects. We can divide our activity like in two different but connected blocks. We have been working in basic research projects. For example, we have started a PhD in TP thermomechanical modeling, combining deep learning and phenomenological models, like physics-informed deep learning. We have also do some research in the effect of recycling of mechanical properties of TPVs. We have published an article with, in collaboration with a colleague from a German university. We also been developing accelerated methods to predict long-term mechanical behavior. We also have started a new collaboration with Wilmars, with Endurica, related with modeling of fatigue behavior of TPs, taking into account the inelasticity that these kind of materials have. And finally, of course, our colleague Iseti will present also some results related with a research project related with the effects of processing in the morphology of the final properties in order to optimize the process parameters to tune the mechanical performance. But these low tier level projects also have a combination of a higher tier level projects. We are collaborating with different automotive suppliers in order to develop innovative approaches using elastomers closer to the market than the previous project. And well, we want to have a combination, the combination between basic knowledge, basic research projects, and projects more related to the market. So this is the whole idea, to develop new knowledge and then try to transfer to the industry. Okay, so well, because of that, we have today in this workshop end users like Renault, Metravip, researching on and developing characterization methodology. We also have Endurica, related with modeling and developing software, and of course the article supporting all the value chain with research in polymeric materials and component characterization. So well, this is just a short introduction. Remember that after the different presentations, we will have a time for discussion, for questions, so you can use the channel, the YouTube channel, in order to send your questions, and then we will present those questions to the speakers. Okay, so well, we can start with the first presentation. We have today with us Brice and Pierre. We can start with the presentation of Pierre Furbergel. Sorry for my pronunciation, I'm not good in spelling. Pierre obtained the PhD at the ECPM in Strasbourg in the bioteam in renewable polyol synthesis from sorbitol to polyurethane foams formulation. He received in 2018 the best PhD award from the French Plastic Engineering Society, and he joined Renault engineering team in 2018. After being in charge of polymer material development and prescription for underbonnet application for 3 years, he is now the technical polymer specialist. Well, Pierre will talk us about the opportunities of TPE materials in the automotive industry. So Pierre, the floor is yours, so go on.
Okay, thank you very much for the kind introduction. Can you just confirm if you see my screen correctly, and I will start right away?
Yeah.
Yes.
Okay, perfect. So good morning, everyone online on YouTube. So my name is Pierre Vingler, and on the behalf of the Renault Group, I will talk a little bit about the TPE future for electrical vehicle and sustainability. I will also mention that this presentation has been done with the participation of Alia Akrout, Gabriel Gauge, and Guillaume Blancard. The presentation will be divided in 5 parts. First of all, an introduction of the Renault Group. I will talk then a little bit more about our green policy, because you will see that it can influence the choice of our material, including TPE. Then we will have a quick view of the electrical vehicles and the fuel cell vehicles. We will end with a conclusion and perspective. So as an introduction, you all know that Renault is producing cars. We own 4 brands. We have Renault, Dacia, Alpine, and Mobilize. And as an OEM, we have many priorities. First of all, it's our customer, the safety, the legislation, the environment, the design of our car, obviously, and the innovation. Since 2020, we have a new CEO. Maybe you haven't been heard about him. His name is Luca Di Meo, and he started a new program called the Renaulution, which is from volume to creating value. For this, he creates new entities inside of the group Renault. So now we start to be divided in several entities. So we have Horse, which has been created in July of this year, which is dedicated to low emission thermal engine. Then we will have Ampere, which is dedicated to electrical vehicles. It should start in November of this year, so in 2 days. And then we have Alpine, dedicated to sport car, Mobilize for the new mobility and service, and the future is Neutral, which is dedicated to the circular economy. Now let's talk about the Renault Group green policy. So as most of the big companies in Europe and in the world, we have to commit for decarbonation. So our road is quite simple simple in word, in theory, in practical not so much, but in 2030, we want to reduce our CO2 emission by 30% and increase by 33% the recycled material content in our car versus 2019. Then we want to reach carbon neutrality for all cars produced in Europe in 2040. And then we want to reach the carbon neutrality worldwide in 2050. To achieve this goal, we have several leverages, and now I will more focus about the material aspect and especially the polymers. So first of all, we will start with this pyramid. So this is the summary of our Renault Group green material strategy. As a philosophy, which means for Alliance specification philosophy. So you can see on the very top of the pyramid in red, what we consider to be the least green solution, so meaning the polymers with the highest emission of carbon dioxide. So in this category, you will find what we call the virgin polymers, so all the conventional polymers we are used to have. And then just under, you will find the post-consumer chemical recycled polymers, so the polyolefin and the technical polymers. This solution today doesn't seem to be too green for us, even if it is a recycled one, because the chemical recycling process still use lots of energy, lots of chemicals, washing step, and so on. So it is not so green at the moment, and it's cost a lot, so it's not very good for us. But this is something we hope it will change in the future. Then, if we are in the middle of the pyramid, we have the post-industrial mechanical polymers and the virgin bio-based polymers. These two categories are very interesting in terms of CO2 reduction, but as you certainly know, post-industrial mechanical recycled polymers cannot go inside the recycled content of our cars according to the legislation. So they are interesting for the CO2 emission, but to decrease the CO2 emission, but not so much to increase the percentage of recycled material in our car. Then, just under, we have the two most important categories for us, the post-consumer mechanical recycled polymer and the end-of-life vehicle polymers. These two are the greenest solution and the two we want to give a big highlight, and especially for the end-of-life vehicles, meaning you is a greenest solution, and it is what is also asked by the regulation. So these two aspects mean that we have a big highlight for these two last categories. Now, you can see on this screen that I'm talking about bio-based polymers. Bio-based polymers is something which is, let's say, quite complicated to accept for us, because we have to dedicate a clear strategy for the bio-based polymers to be sure not to go in a wrong direction. By this, what I mean a wrong direction, we built a strategy which is based on the sustainable goal of the United Nations. It's a consensus. It is not a norm or a standard. And what we decide is that we decide not to use all the biopolymer based on edible biomass. This is what we call material from generation 1. You can see here on your screen. We don't accept this kind of material because there is a competition with the food chains, and so we cannot accept to have any polymers from this category in our car. We don't want to have people asking why Renault is starving population just to produce cars. So this kind of material, if you have a biopolymer made from corn or from whatever you want, from sugarcane, we cannot accept it. I'm sorry for that. The other generation we have are generation 2A, 2B, and 3. This generation, I think you start to know this denomination because we are not the only one to use them. So we can accept what we call material from generation 2A. It's by-produced in parallel of generation 1. We will always ask proof of traceability and sustainability, because it's okay to use byproduct, but we don't want to create an excessive production of one specific crops in the world just to have the byproduct, because it will make not a good balance between the production, and we cannot accept that neither. So it is okay for us to have this material, but we need to investigate and be sure it is completely right according to our specification. Then we have material generation 2B, cultivated on arable wooden soil. So likewise, we'll just check if there is no deforestation, for example. And generation 3, produced without direct usage of the soil, such as algae, something we are really wishing for, but it is not very current today. So here you have the Renault bio-based strategy and what we can accept as a material for our car. Obviously, it is for all polymers, so you can understand in this, it's for thermoplastic, it is for rubber, but it is also for TPE. Now, one thing is missing on this slide. If it is about the mass balance approach for the bio-based product. Several times the question is asked. So just let me explain also what we can accept or not in the mass balance approach. So for the mass balance, we will start with what we decline. So with the kind of product we cannot accept in Renault. So we will decline all the credit method, meaning, just to give you a brief explanation, if you have a product here, whatever the product is, in the chain production, you have two feedstock entry. One is bio-based, The other one is fossil-based, but you have a freedom of attribution of the bio-based content in each product. So for example, the first batch is 100% bio-based, the second one is 5%, the last one is 0%. It is something we cannot accept because it is a kind of a lie. Actually, you have the same number of bio-based content in all products, but just by a credit, you can say this one is 100%, this one is 0%. So one customer will have 100% bio-based part and the other one will have the 0%, which is completely false, sorry, because in both parts we will have the same number. So we cannot accept the credit method. The other method we cannot accept, it is almost the same thing. It is a book and claim method. In this case, you have a plant working with 100 bio-based feedstock. The second plant is working with petroleum-based feedstock. And then there is a credit transfer from plant 1 to plant 2. So this is the result is the same as the conventional credit method. You have a bio-based content which is just a credit, not the reality, so we cannot accept it. What we can accept, it is much more interesting. It is everything where you can control the bio-based content, for example, with carbon 14 measurement, and you have the truth inside your product. So we can accept what is called the rolling average percentage method. This aspect of the mass balance is very simple. You one more time have your two feedstock in entry, the bio-based one, the fossil-based one. The only difference you have, all products are sent with the exact content of the bio-based inside the product. There is no credit, but the percentage of bio-based can have some variation during the year because your bio-based feedstock is based on a production with a variable amount during the year. So for example, in August, you have 15%, and in September, only 5%, and December, only 5%. It's okay as long as we know the exact percentage all along the year and all along the production. And the last one I will present for the mass balance approach, and is the one we like the most, is the control blending model. In this case, whatever is the production chain, you have two feedstock. One is bio-based, the second one is fossil-based, and the content is stable. All the production will have always the same percentage of bio-based and fossil-based. So this is a quick summary of what we can know about the mass balance approach. If you want more detail, you can check the ISO standard, but here you have a quick summary of what we can accept. And one more time, it is for all polymers, including the car production, so thermoplastic, thermoset, rubber, and TPE. As a conclusion, we do not focus on what we don't want. We want to have a clear positive view. We will accept everything which allows to have true CO2 avoidance. We accept the mechanical recycle, the renewable polymers, as long as it's generation 2 and 3. We accept the post-consumer recycled material. We accept the chemical recycling. But what we cannot accept is no credits method. We always want to be as close as possible to the truth. And we also cannot afford to have overcost on the material because it is bio-based or recycled. Our cars are already expensive enough for our customer. Now let's talk a little bit more about TPE, especially so the TPE in electrical vehicles and in what they can help us to the decarbonation road, how they can help us to decrease the CO2 emission. So here you have an electric car, and the main difference with the internal combustion car, the conventional one with the classical engine, is before to decrease the CO2 emission, you just had to decrease the weight or decrease the engine consumption, and it was okay. You were decreasing your CO2 emission. With an electric car, it's much more challenging because you have to work on the car assembly and maintenance, on the low emissive polymers and metallic part, low emission oil and grease, and you have also to use all the bio-based material, recycled one, green chemistry and processes, for example, in the battery, and also the bio-based coolant. So the strategy to decrease the CO2 emission of an electrical car is not the same as for an internal combustion engine car. To give you a quick overview of what we have as a TPE part into our car, we have several hoses. So they are mainly in TPV. They can be recycled or bio-based compound with a low global warming potential. Low global warming potential because in most of the case they will replace EPDM, and EPDM, because of the curing step and the process, which is more close to a batch process, we have higher emission with EPDM. So each time we can replace EPDM by TPV, you decrease the CO2 emission of the cars. The main thing we will ask is to have good edging property in contact with air or coolant, because most of the TPV hoses are used or should be used on the coolant line. Another application, which is still an under bonnet application, is just in front of your car. You will have all in this area, all the air guide to let the air go in your under bonnet area, and then to have the good flow inside. So these air guides are generally rigid one in thermoplastic, but we always have on the edge, just here, TPS or TPV overmolded compound. This acts as a kind of sealant to have a good adhesion between the aesthetic part of the car, so the front of your car, and the interior of the car. So here, this thermoplastic elastomer, whichever they are TPS or TPV, are not so much solicited in temperatures or in mechanical strength. So we are mainly pushing to have recycled compound. We still, the only thing we need is good overmolding property, especially on polypropylene frame. Last option we have under bonnet here, and I will present, is something which is maybe not too common now, but not so much used, but we can think about all the electric parts. We can have TPE in the electric wire, on the bus bar, or in the connection. We will go back to the electric part just in the next slide. And then other application can be all the sealant from the door, for example, and the carpet inside of the car, which can be in TPV, TPO, TPS. For the carpet, we are pushing a lot for the recycled material, especially for the end-of-life vehicle recycled material. And one thing which is quite challenging for this carpet, even if it seems very easy because you just put your feet or your luggage on it, we have to be sure that there is low odor emission, because you don't want to have an odor of plastic in your car, and with recycled material, sometimes it's quite a challenge. So here was the overview of the main TPE part we can use. There is plenty of other, of course, but we cannot go through all of them. And just to give you a quick focus now on the electrical, part dedicated to electrical vehicles, because hoses, cooling, air guide, carpet, sealing, we have it in all our cars. So now just let's go typically to the electrical vehicles. It is important with the electrical vehicles, first of all, is the legislation. So here you have this small car, which is not going very well since there is smoke. If, unfortunately, a car has an accident, whatever it is, a crash or a defect, there is a legislation which says that after the thermal incident, because you often have a thermal incident in your battery when you have a crash, you cannot have smoke inside the passenger cabin for at least 5 minutes to let time to the passenger to go out of the car, basically to escape. So what can be at the origin of this thermal event, which can create this kind of incident in your car and in the battery? Especially it is coming, for example, one example which is an interest for us here, it's not the one, but it is one we are talking about with the TPE, is what is the additive package you are using in the TPE formulation. We cannot use TPE close to the electric part or to the battery, which have copper halide or red phosphorus inside the compound. Why this? Because with the water, you can have migration of the copper ion, and this can allow transfers of electricity between two parts. If this part, unfortunately, one is close to the cathode and the other one is close to the anode, you will have a short circuit. So it is not good because you can have also other problems such as corrosion, dendrite, and heating. So this is what we cannot accept and which is important when we are talking all together about TPE for electrical vehicles. If it is close to the electricity, let's say it like this, we have a need of high flame retardancy to avoid the propagation of the fire and the smoke, but we cannot have red phosphorus as an ignifuggant, as a fire retardant, sorry, because if you have red phosphorus, it can create an acid with humidity, and we have corrosion of the metallic conductor, so we are in this case here, and we cannot have copper halide, it's stabilized for electrical and electronic application because we are afraid of the potential current leakage it can goes with. This is the only one I will show about specifically for the electrical vehicles. Now I will give you the opportunity to have a quick insight of the fuel cells vehicles and what are the challenges and requirements for the TPE in the fuel cell vehicle. So, as a short introduction, if we make a comparison between the fuel cell and the conventional electrical vehicles. First of all, the temperature of usage are not the same because for battery, if you are above 60, 80 degrees, your battery basically is dying, it's not working well. So the battery is cooled with actually a conventional water glycol coolant, especially with bottom plate under the battery. We can imagine also dielectric coolant for direct immersion of the battery, but it is not used currently in Renault. What is the main challenge for a battery? It is not the temperature, as you can see, but it is the high solicitation, especially of the cooling circuit, because you are cooling the battery when you are charging and also when you are discharging the battery. So you are almost always using your battery in an electrical car. So what can be the challenges for TPE? It's TPV with recycled hydrolysis resistance, TPV with multi-layer hoses, and all this connection to the battery, whatever, if they are mainly quite focusing about the cooling system because this is where you have most of the TPE, but it can be another part. It has to be very well designed to be long-term hydrolysis resistance or long-term aging data, because even if the temperature is not so high, it's used most of the time. Second aspect is for the fuel cell. So with the hydrogen, what is the difference with the fuel cell? Currently, the fuel cell temperature is starting at 80 degrees. It will certainly improve in the future to increase the yield of the fuel cell, but let's say that today it's 80 degrees. What is very important for the fuel cell, I mentioned here the coolant, but it is also true for the other circuit we will see just after it. It is to have a low conductivity water glycol coolant. So what? Because we don't want to have interaction with the fuel cell and the conductivity of the coolant. So it is important not to increase the conductivity of the coolant. So one more time, such as with the electrical vehicles, here the compounding of the TPE will be very important because we can have whatever you want, TPV, TPE, multi-layer, but what we cannot accept is to have an extractable content. So we want TPE with low extractable content to be sure that we will not poisoning the fuel cell. Let me explain a little bit more about the poisoning of the fuel cell. So just start with how basically the fuel cell works very quickly. On one side, you have an entry, which is from the hydrogen tank. So you have the hydrogen coming. It is not at the pressure of the tank, obviously. It is only 2 bars with 100% relative humidity. It's at the anode. At the cathode, on the other side, you have the dioxygen from the air. Also 100% relative humidity and 2 bars of pressure. And the last circuit you have very close to your fuel cell is a cooling circuit with a conductivity which is set at a maximum of 5 microsiemens per centimeters, and we have a very high cooling rate. All this circuit, there is hoses. These hoses can be in TPE. It is not a problem for us. I think that 2 bars, it's okay. 100% relative humidity, it's not a problem. But what is a problem with the humidity, whatever it is in the oxygen, in the hydrogen, or in the cooling circuit, is if you have leaching from your material. So if you are taking some ion, some impurities, which will go inside of the fuel cell stack. Why we don't want to have this type of contamination? Here are the example of contamination that you can have. You can have cationic impurities, organic compound, or anionic impurities. Cationic impurities are mainly ion, extracting leach from the compound. Why they are quite bad for us? Because one of the main catalysts of the fuel cell is a platinum. So if this metallic catalyst is poisoned by one of the cation, it will not work for the fuel cell. It will work to create another reaction or whatever we want with these impurities. So it decreases basically the yield of the fuel cell. This cation can also interact with the membrane, which is a polymeric membrane inside of the fuel cell currently. So we can have interaction with the porosity of the membrane and decrease also one more time the efficiency. And one cationic impurity, what we really don't want is 3+ stage of oxidation, because this one is the only one which can create a degradation which is not reversible, because if you have a contamination of the catalyst, a contamination of the membrane, you can imagine that you can wash it and recover your fuel cell. But with the ion 3+ stage of oxidation, you will initiate the Fenton reaction on the membrane. So the membrane is degraded, and so you are really losing the first time your fuel cell. So it is really not good. All the organic compound is mainly from the monomers. So here I have example with aniline or caprolactam. Caprolactam is more from the polyamide world, so maybe a TPA. It's not so common, but whatever you have as monomers going inside, we have the same kind of problem. You can have platinum contamination. As the platinum is involved in many chemical reactions, it will be occupied to do something else than working for the fuel cell. And we will also have a loss of the kinetic and the efficiency of the fuel cell because of the membrane, which will be impacted by this compound. And the last category I will show you here is the anionic impurities. Anionic impurities such as the halogen, for example, which are coming from the specific compounds. We will also have interaction with the catalyst. So here, my big, let's say, message to you is that in case you want to use TPE for fuel cell, what is very important beyond all the conventional aspects, which are the mechanical property, does it work, doesn't work? Well, we also have to think about the contamination of the fuel cell, and the contamination is often happening with the material leaching ion because of the water, because of the flux of water inside of the hoses. In this specific idea, we start to initiate a protocol in Renault to try to investigate our materials. We share it with you because we don't know if it is the best one, so we are always waiting for feedback, and we are glad to share it if you think it is a good one also. You can use it. So we are taking samples to try to have always the same surface of exchange between the sample and the media, and our media is ultra pure water. We are using ISO standard for traction, so the ISO 5271A, we cut it in 2 pieces, and we put them in 250 milliliters of ultra pure water in a glass bottle with a cap, and the cap must have a sealant which is not paper, otherwise you have contamination of the water. We've set the temperature at 85 degrees, and we have aging time up to 1000 hours. Basically, it just looks like this. The purpose is to have something which is as easy as possible, to be very practical, and to have a good screening of all the TPE compound we can have. So in this case, it's all of them are TPE. And what we do at the end of the aging time, we test mainly the water. So we test the total organic content to investigate the global ion release. We also perform ionic chromatography to investigate the anion release. and some inductively coupled plasma to investigate the cation rays. For us, this is what we are doing at the moment, and the final purpose is just to have a conductivity measurement to say, okay, if we reach this value, it is not okay, we have too much ion, cation, and release into the water. So today we're investigating everything, and the purpose at the end is to have a very simple test with just a conductivity measurement. Now let's jump directly to the conclusion perspective. So as a conclusion, you understand, I think, that we work with lots of polymers in the car, lots of TPE, and our main goal is to decrease the CO2 emissions. So our main challenges today are to decrease and use the TPE at the right place with the right formulation and the right content of recycled material or bio-based content, as long as it is not generation 1, no book and claim, and no credit method if it is mass balance. The development and the application are on the fuel cell application and the testing method related. And what we call the technical challenge is a long time projection, aging, creep, fatigue. You can think about the battery we saw in the third part of the presentation, the hydrolysis resistance, it's working for everything now, and which level of purity is required for hydrogen application, and material compatibility. We didn't speak about it in this presentation, but what is the material compatibility with pressurized hydrogen, especially at the outlet of the hydrogen tank when you are depressurizing from 700 bars to 2 bars? What is happening? Is there any cavitation, or what can be the impact on the material? This is the last slide of my presentation. If you need to contact me, you have my business card just here. Thank you very much. I hope you enjoy the presentation. And if you have questions, I don't know exactly how it works, but I will be glad to answer.
So, well, thanks, Pierre, to fit to your time. It was exactly half an hour, so that's great. Okay, so, well, it was a very interesting presentation, and you have been presenting that you are focusing more to the, or you are neglecting or refusing first generation bio-based materials. About the second generation, which are the most appropriate ones from your point of view, and which could be the applications for this kind of biopolymers.
So in this case here, well, I can give you, I think, example with the, I have idea with polyamide or with the cooling also. So with the polyamide, you have everything based on castor oil, which is okay because this plant is clearly growing on an area of the world where you don't have crops for humans, and there is no interaction with the environment where it is cultivated. Another topic could be the coolant, because I talk also about the fluids, because I'm expert for the polymers, but also for the fluids in Renault. So you can have coolant development where the monoethylene glycol is coming from wood. And the most thing we also have to be worried about, if we are talking about TPE, is in TPV, you often have the EPDM, which is bio-based. But the EPDM, when you are going back to the beginning of the chain, they say there is no competition, but in most of the case, it is coming from the ethylene. The ethylene is coming from sugarcane. So yeah, here we have to be very careful with what is considered as a byproduct, because for some people, sugarcane can be a byproduct because they are using it after being pressed to collect the sugar, but we do not accept it as a byproduct because it increases or use the sugarcane not as it should be used. So there is pros and cons for everything. Yes, in most of the case, because of the volume or the production, which is not the most conventional one, we have a slight deviation of the price. And we are working, not me, because I'm just looking at the property of the material, but we have a whole team of buyers and people in charge of this who are working with the supplier to fit at the most appropriate price.
You showed in one of the slides. So they are asking if this TPE solution is something that is nowadays implemented, or is it a potential application for TPE materials?
Okay. Some of them are already implemented, especially the overmolded TPE thing on the frame of the air guide. For the carpet, it is also implemented. For the sealant, it depends on the car, honestly speaking. And what is quite really in development, it is the hose for the cooling system. It is not because it is new or because it wasn't working before, but in the past, EPDM was really the king of the application. And now we start to have more and more projects with a solution TPE for all the hoses. So I'm focusing on cooling hoses because this is maybe the biggest amount of TPE we can find in. We can also have some hoses for the air circulation, especially the corrugated hoses in TPE with good elasticity and things like this for the noise emission also, because it can help to reduce the noise emission. I think you know something about it in the article. So we also have this in the project. So maybe more future or incoming application, because not because of the technicity, but because of the novelty and project here. This is already used, this is already used, and here for the electrical, very close to electricity for the busbar and so on, it is more prospection today.
I think we don't have more questions, so I think we can continue with the presentation from Metrabip.
Yeah, okay.
Thank you, Pierre.
Thank you very much. Bye-bye.
Thank you very much.
Thank you.
Bye.
We stay for all the meeting, of course.
Yeah, sure. Okay, so well, the second presentation today is coming Tyler, and he's the general manager of sales of characterization instruments. And now, well, she's the manager of Metrobip, and he's coming today presenting some new developments related with DMA analysis and dynamic mechanical analysis. So he's going to talk about some basics and also some applications. So, Bryce, the floor is yours.
It's up to sound is okay, and the image as well. Okay, so let's do it. Thanks for the introduction. I'm Brice. I'm the general manager of Metrobip Material Testing, and the aim for me for today is to give you basic ideas regarding dynamic mechanical analysis and focus on standard application as well. So the summary of my presentation, I would like to give you an introduction of a DMA, some basic elements regarding DMA application, fatigue application as well. I would like to concrete this application by a case study. And of course, to conclude the presentation, I would like to introduce the Metrobip range of products, what kind of DMA we are producing, for which kind of industry or which kind of material testing. So DMA introduction. Just to that short introduction, DMA is a major non-destructive techniques for measuring viscoelastic properties, and this techniques is covering many industrial applications right now. For instance, in our business, maybe 50% of our customers are focused on tire industry, and DMA instrument are used for tire performances. More and more, we are working so closely with sport industry, with leisure industry, and one main application of DMA is to concrete sole shoe, as you can see at the image. We are working also for trucks industry, especially focused in Canada and in US. More and more, we use the DMA to characterize composite materials, brake pads, for instance, polymers as well, and in medical field with a good example from heart valves. So, what is DMA? DMA is really useful to characterize first glass transition of polymers. Maybe 80% of DMA use is focused on glass transition determination. More generally, the idea is to characterize the response of the materials to application removal of a load. When I'm talking about load, I'm talking about dynamic load with a combination with a static load as well. DMA is really useful to characterize the linear and non-linear behavior of elastomers, the frequency dependence of the viscoelastic properties, of course, and more generally, the thermomechanical behavior of the material over a wide temperature range and its dependence to other environmental effects such as humidity, for instance, such as inert atmosphere or so many effects. So, how DMA can help researchers and engineers? First, we are able to understand the relationship between the material's molecular structure and its mechanical properties. DMA can predict how the materials will perform. We can select the right materials to obtain products' expected performances, and we can control the key performances of manufactured products in their condition of use and ensure the manufacturability and lifetime. The working principle is quite simple. You have a basic schema of a DMA instrument, DMA plus 1000 right here. We use an electrodynamic checker, and this electrodynamic checker is able to apply a dynamic displacement to a specimen, and we are able, once again, to record the dynamic displacement signal and the force signal as a sinus signal. With the displacement and the force signals, we are able to compute the stiffness of the materials. It's just a force under displacement. And regarding the shape factor of the specimen, that is to say, if we are working in tension, in bending, or in compression, in shear mode, I don't know, with the modulus, we are able to compute, with the shape factor, we are able to compute the modulus. And the tangent delta is just simple combination between loss factor and E modulus. And tangent delta is just representative of damping properties of your materials. DMA introduction, working principle, quite simple. So modulus is just stress under strain, and we have an elastic part and we have a viscous part in the viscoelastic properties. Elastic storage modulus is to express the ability to store energy. Modulus is about to express the ability to dissipate energy in heat, definitely. And tangent delta, the materials damping. This is a viscoelastic spectrum, for a typical amorphous polymer versus as a function of temperature. And in DMA, we are able to characterize the glassy plateau, the transition region, of course, with primary transition, such as glass temperature, for instance, the rubbery plateau, and sometimes, depending on the instrument we can use, or depending on the kind of materials we are able to characterize, we can also characterize the viscoelastic and the liquid part in the final region of this spectrum. Okay. As explained, we are able to test materials according to a few excitation mode. First is tension, compression, in shear, and in bending. Of course, we have a lot of different excitation mode, but the most basic are this one. And the DMA is quite very flexible analysis technique to address a large variety of materials, thermoplastic, of course, thermosets, rubber, metal, ceramics, more rarely, I have to confess, film, paste, and even liquid. So DMA application. The aim in this part is to introduce some very basic application of DMA with one example each time. So, as explained, first reason we use DMA is to characterize glass transition. As you can see on this image, we use compression plates on a standard rubber. We apply a temperature sweep from -70 degrees up to 15, 20 degrees. And the aim is to characterize the tangent delta, the peak of tangent delta regarding the glass transition with different frequencies. Okay, so this is for determine the effect of additive, filler, and to have a relation between the final application of the materials regarding the technical consideration of the test. Okay, this is one single test actually, and we are able to modify the frequency during the test, and we are able to have different tangent delta peak as a function of the frequency. One other important test in DMA is strength sweep, and strength sweep is to visualize, to characterize the linear behavior or the non-linear behavior of the materials. And the non-linear behavior, as you can see, we can name it the pain effect. And of course, if we are able to characterize the pain effect, we are also able to characterize the Mullin's effect. So in red, you have the dynamic displacement applied by the DMA. Very low displacement, plus or minus 22 nanometers, and at the final plus or minus 2 millimeters. And as you can see, we have a linear behavior and we have a non-linear behavior. And if we are looking at the green curves, we also observed a maximum of tangent delta as a function of dynamic strain. Frequency sweep right now. Frequency sweep is quite common common test in DMA. Quite simple. We would like to characterize materials frequency dependence. Okay, so we are able to perform from very low frequency to a very high frequency. The aim of this illustration is to show frequency sweep from 0.002 Hertz up to 1 kilohertz in one single measure. Of course, in strain control, in compression mode. Okay, and the aim and the advantage of DMA from Metrib is you are able to perform this test in one single measure. One other application, quite important, is the capability to compute master curves. Master curves is just the ability to have prediction of properties beyond testing DMA capabilities. As explained, in DMA plus 1000, for instance, the maximum frequency we can achieve directly is 1 kilohertz. But sometimes in industrial life, we would like to characterize viscoelastic properties over 1 kilohertz, maybe 10, 20, or 50 kilohertz, for instance. So the only way to have viscoelastic properties for such frequency is to compute master curve. Master curve, we just apply some frequency sweep under different temperature stages, and with some algorithm, we are able to compute this kind of curves. Okay, so this example is the evolution of E prime and E double prime and tangent delta as a function of reduced frequency. And here, for instance, you have 1 kHz, 10 kHz, etc., with the WLF coefficient named C1, C2. It's all about theory, but we have the total and automatic algorithm to do it quite easily. One other test, temperature ramp, but on tires. And I would like to show you these curves. Actually, we are working so closely with Michelin or with Continental, Bridgestone, Pirelli, and DMA in such cases are used mainly for this kind of thing to have the tangent delta, to get the tangent delta as a function of temperature, because actually tangent delta is a key predictor for tire performances prediction. That is to say, the wet grip or the rolling resistance. And here in green, we have a tire with silica, for instance, and in black, you have a tire with carbon black inside, just to have the comparison regarding the grip in wet condition or the rolling resistance. One interesting curve as well is the characterization of different kind of tire, winter tire, summer tire, and all-season tire. And you can see the tangent delta of this tire as a function of temperature. And you can easily imagine why it's really clever to use summer tire in summer and winter tire in winter, actually, because of the position of the tangent delta. And the position of tangent delta is, of course, depending on the performances of the grip of tire as a function of temperature. Okay. One other, it's quite new for us, the pull-out test. Pull-out test is just the ability to characterize the adhesion between a rubber matrix and cords. This kind of test is mainly focused for tire industry, once again, but you have the possibility to apply a dynamic mechanical force and a pure static force if you would like to perform a creep test, and to get the static displacement or the static force or the dynamic force between the start of pull out and the end of the pull out test. So it's quite a new functionality available on DMA. So what about fatigue application? Just as a short introduction, in industrial application mechanism, and we would like to understand this mechanism. Okay, so we have one software able to compute and able to handle DMA testing and fatigue testing, named DYNAeLAST, and we are able to provide a lot of fatigue capability. I would like to just introduce 3 of them. The first one, as you can imagine, is just standard fatigue testing. That is to say, the evolution of the modulus as a function of the cycle number. I show the example of a snowboard in a bending mode. Sorry, 3-point bending mode. Apply to high force test, plus or minus 200 Newton with a frequency of 40 Hertz and number of cycle also 300,000 number of cycle. As you can see, if you are looking at the red curve, that is to say the evolution of E prime as a function of number of cycle number, we don't see anything interesting. But if we are looking at the blue curve, that is to say the evolution of tangent delta, you can see that above 100 cycle, something happened inside the materials, and after a picture, we can see the beginning of the delamination of the composite sample. So DMA can provide some quite precise information regarding the failure mechanism for a testing specimen. One other application is the crack growth test and the automatic crack growth test. And the aim of this test is to get the crack growth rate as a function of the level of energy applied. Okay. The composition is quite basic. We use an optical system with a micrometric motorized table with a lens magnification, and we are able with this to characterize a crack tip position with a precision of 5 micrometers. We use for this a high resolution video camera, and we are able to work with this kind of specimen, 2 dimension available, 40 millimeters lens and 80 millimeters lens. And with this larger specimen, we are able to follow 4 cracks at the same time. So the aim is quite simple. We apply a strain, a dynamic strain with the DMA. We can combine with a static strain as well. We start to propagate the cracks, and the camera is able to find and to record the growth of the crack tips, okay, automatically. The aim is to get the evolution of the crack growth, that is to say the red curve as a function of number of cycle, and with the length of the cracks, we are able to compute, to calculate the speed of the cracks, the crack growth rate in nanometer per cycle. Okay, and we are able to get this kind of diagram, and this one as well, that is to say the level of energy as a function of dynamic displacement. This is peak to peak in meter. Okay, so we are able to automatically chain different level of energy in one test. We're able to determine the lowest energy for crack propagation, and we are able as well to determine the highest energy that a material can handle before rupture. You can see a short animation with this kind of test. Okay, one other interesting test is yield buildup test. Yield buildup is to characterize the self-heating properties of materials. We use for this fatigue testing with high strain rate. We use a specific specimen order, okay, in order to get the temperature just on contact on the plate on the rubber specimen, and we apply a fatigue test, and after the fatigue test we inject a needle inside the specimen in compression to get the internal temperature. That's the evolution in green that we can see on the illustration. We finish the fatigue test at 66 degrees, and after pushing the needle intern the specimen, the internal temperature is above 125 degrees. Okay, it's just to characterize the self-heating properties of your materials. Once again, really focus for rubber, of course, and really focus for tire industry. So case study. I would like to introduce a case study focus on squash ball. Actually, I would like just to explain how the DMA can be useful on the concrete test. For this, we ask to Decathlon. Decathlon is one of good customers, quite partner actually with Metravib. They provide us 3 kind of smash balls, beginner one, intermediate one, and expert one, with classic configuration. The beginner is really often used when you're starting squash for initiation. It bounces, it's really easily, and we don't have to need to preheat the balls before taking advantage of its rebound. As you can see on the blue curve, the rebound is quite high. As the opposite, the expert is the official ball for squash tournament, and its bounce is really low, and the expert ball require a warm-up period of 5-10 minutes to be playable at its full capacity. So the aim is to obtain the correlation between the rebound capacity of a ball and the mechanical properties of materials. For this, I introduce you my dear colleague Mathieu. For this, we drop the beginner and the intermediate balls at the same height, and of course you can see that the blue one show a much higher bounce than the expert one. Just to compare expert and beginning balls. If we compare the same ball but not the same temperature, we can see that the hottest ball, this one, the bounce is really high in comparison with the standard temperature one. So once again, how to translate this observation into a measurable experimental parameters in DMA? So for this, we use a DMA plus 1000. We apply a dynamic displacement of plus or minus 50 micrometers. That is to say, in the linear behavior of your materials. No static force. The balls were glued between compression plates. We use a frequency of 20 Hertz, and the temperature range was minus 70 degrees up to 100 degrees. We apply a temperature sweep. As we can see, the evolution of the modulus E prime as a function of temperature on the three balls. I just located the operating temperature range during a match. And just as a reminder, E prime is the ability to store the mechanical energy supply. And for this, we observe no significant difference. Okay, the same for E double prime. E double prime is a loss factor. Once again, I located the operating temperature range, and E double prime is the ability to dissipate energy by heat generation. Okay, E prime decrease with the temperature. The rebound is getting higher and higher. That's totally normal, and it's not really obvious, but the expert ball dissipates more. The bounce is logically lower, as you can see here. More interesting, if we are look at the tangent delta. Tangent delta is ability, it's a factor corresponding to damping properties. Okay, once again, the blue, the beginner, the red is the intermediate, and the yellow is the expert one. We can see that the balls formulation have two distinct compounds because we observe 2 TG peak, okay? And the proportion of these compounds is quite different and depending on the ball's level. And this, we have to look at the dynamic of the TG peak for this. The first peak is higher for the beginner ball, while the second peak is really higher for the expert ball, influencing the viscoelastic properties. So expert balls with a higher viscous component bounce less than beginner balls, which are characterized by more elastic behavior. It's quite obvious. Then we apply hill buildup analysis to get the self-heating properties, as you can see on this animation. Testing condition is 25 Hertz and dynamic displacement is plus or minus 2.5 millimeters. And we perform this test on the beginner and the expert one, and this is the results. The evolution of the temperature at the surface and at the final of the test, we inject the needle to get the internal temperature. The gap between the surface and the heart of the specimen for the yellow one was 12 degrees. The gap is much higher for the beginner one because the gap is about 20 degrees. So once again, the beginner gap is higher than the expert one. This is totally logical because the expert ball is more viscous and therefore it's more able to dissipate. So we can easily show this aspect with this kind of test. Last test we perform on this is exploiting the temporal signal. The temporal signal is dynamic force as a function or dynamic displacement or dynamic stress as a function on dynamic strain. The aim is to visualize and to get the hysteresis loop to get once again a more accurate analysis on nonlinear behavior. Okay. We allow to control the wall excitation history, and the shape of the loop could indicate the nature of the damper. the damping, sorry, and it could allow the energy calculation within a cycle. And of course, the loop for a beginner barrels, it's much different. It's really different in comparison with an expert one. Okay, our range of products. I would like to introduce our range of products because we are talking right now about DMA plus 1000, but we are producing such different DMA instruments. We have three kind of different family for this. The low force DMA named 25 and 50. It's just quite DMA, low force DMA, really easy to use, very convenient. It's really cost-effective solution for this. We are able to perform all DMA standard characterization, such as frequency sweep, strain sweep, temperature sweep, master curve computation, creep relaxation test as well. On va dire, our main customers for this is university, private laboratory, and the aim is to have a pedagogic vision for this application. DMA Plus series, it's a high-end DMA or high-force DMA. We have three different instruments named DMA Plus 300, 1000, 2000, depending on the level of dynamic force available. DMA plus 300 is plus or minus 150 newtons, for instance. For DMA plus 2000, it's plus or minus 1000 newton. This range of products, it's much complicated than DMA 25 and 50 because we have additional capability such as fatigue testing. We have another excitation mode available. We can robotize this range of products with expander. The aim of expander is to load and unload automatically specimen into the thermal chamber in tension, compression, and shear mode. Okay, and we can add some very standard specific applications, such as crack growth, such as hill buildup, and much more. One last family of DMA is named VHF 104. VHF is for very high frequency, and 104 is for 10 kilohertz. As explained, the maximum frequency we can reach with DMA Plus series is 1 kilohertz. With desktop series is 200 hertz. And if we want to go further above 1 kilohertz, we have to compute master curve. For this, we have the VHF, and VHF we are able to get the viscoelastic properties of materials up to 10 kilohertz in a direct way. Just to explain, to compute master curve in DMA requires maybe 5 or 6 hours of test with a lot of liquid nitrogen consumption. And for VHF, we just need 15 minutes to get the whole viscoelastic spectrum up to 10 kilohertz. So it's much more convenient. But the limitation is the shape factor because we are only able to work in compression mode. We don't use any tension mode or in any shear mode with VHF. That's a limitation. Okay, as a conclusion, DMA, we can get the modulus in E prime, E double prime, or G prime, G double prime, depending on the excitation mode we can use. We're able to compute the tangent delta. Tangent delta is a unique factor to determine the damping properties. Glass transition are main application for DMA, but we are also capable to get the pain and the Mullin effect, the frequency effect, the curing process, because we are able to work on resin. I didn't show any case on this, but we can have some reticulation follow-up during a temperature stage, for instance. Static tests, we can use environment, we can control in an immersion, in humidity, we can compute master curve, and we can compute master curve, but in creep this time. We can also add some fatigue capability in order to control the waveform, for instance, with the hill buildup, with hill buildup and flexometer at the same, with crack growth as well. And now the system is fully automated to get the tearing energy. And of course, we can also add an expander to robotize DMA testing and to chain DMA and fatigue testing as well. To go further, I just take the advantage of this DYNAeLAST events to introduce our new DMA white paper. Actually, we built this document a few weeks ago, and it will be released on our new website by the beginning of November. Please be my guest. Feel free to download it. We bring a lot of information regarding DMA technology. We bring information regarding how to use correctly DMA instrument, and we can also produce a lot of golden rules to operate easily DMA. For this, we can get in touch directly in our website. You also invite to contact my Liartiker friends if you need it, or directly me. You have my address email right here. And the last sentence is for our service testing. We are in France. We are based in France, in Lyon. It's quite a nice city. And we have the laboratory with a wide range of DMA instrument, and also the wide range of instrument can be used. We produce DMA testing. Feel free to ask. Many thanks for your attention. I will be glad to answer your question if you have it.
Okay, so thank you very much, Chris, for fit to the time. And just to a short comment, we have some issues with the chat in the YouTube channel. So if you have any question, you can just write us an email, and then we can, or even ask right now in the workshop, or otherwise we can send you the answer by email. And we apologize for this issue. Okay, so
yes, I think it was a great presentation showing the potential of DMA on how to predict and analyze the thermomechanical behavior. And I think we can also link the DMA applications, even if now you have presented the squash ball applications, we can link these applications with automotive, because Pierre has also showed some potential issues related with fatigue, aging, and for sure DMA would help in these challenges too. So in terms of questions, I think I have one. Someone has sent me a question by email, and it's related with dimensions, I think. So someone is asking which are the standard dimensions for testing a specimen on a DMA machine.
Yeah, that's a good question, and of course, it depending on the excitation mode we are able to use. The standard dimension for tension and compression is 8 of 60 millimeters. Diameters may be between 5 millimeters up to 20 millimeters for compression, and in tension, the standard dimension is 60 millimeters 8. 20 millimeters large, and with a width of 2 or 3 millimeters. Of course, it's depending of the capability to get correct specimen. Sometimes we can easily understand it's quite complicated to have a correct specimen. We can adapt, of course, with some limitation, of course, but keep in mind that DMA is quite a flexible technique of characterization, and for sure we find a solution. We will find a solution to have an adaptation regarding the specimen for DMA testing. For shear excitation mode, it's really easy because we use paste of materials. Diameter is 10 millimeters diameter, and the thickness is about 2 and 3 millimeters. And bending mode for TPA, TPU, or composites materials, we are able to work with large specimen up to 130 millimeters of large, actually, with a thickness about a few millimeters up to 10 millimeters. But we have to be careful to be representative between a specimen and the materials in this common use.
Okay, thanks. Well, we have another question. In that case, it's related with the temperature. So, which could be the temperature range that we can achieve using these techniques?
Okay, temperature range is quite important to understand because of the glassy plateau and the rubbery plateau. For instance, we have two ways to decrease the temperature in DMA. One, maximum temperature. Once again, depending on the thermal chamber configuration, if we use a window, if we use an infrared window, or if we use a totally closed thermal chamber, the maximum temperature we can achieve inside is 500 degrees. So minus 150 degrees with liquid nitrogen up to 500 degrees. And we have an alternative, a secondary cryogenic source named air chiller, and the air chiller, the minimum temperature we can reach is minus 70 degrees inside the thermal chamber, and the main advantage of air chiller is to use only compressed air without any liquid nitrogen. So once again, depending on the needs, depending on what kind of materials we are talking about, and depending on the requirement for installation in a laboratory.
Well, we don't have more questions, but I have one question from my side. As in DYNAeLAST, we are targeting elastomers and dynamic applications. Which would be the excitation mode or the to be applied in elastomers if we want to characterize elastomeric materials?
Okay, once again, depending on the needs, but more commonly, shear excitation mode is a perfect one, compression as well, and tension, of course, as well. If we are talking elastomers and dynamic properties, we are only thinking about tire industry. And for instance, Michelin is used shear mode, but Goodyear, for instance, are more focused on tension and compression. Pirelli, depending on what kind of tires they would like to test, but the more common one are shear, tension, and compression.
Thank you, Brice, for the clarification.
Okay, thanks. Well, just a short remark. Also, I would like to remember that we used to organize every year a training course in collaboration with Metravip, and also with Endurica and Wilmars. And those training courses they have a theoretical part just to understand clearly which are the principles that are behind of all those characterization techniques, and then also we have some practical time. We have practical time in order to put in practice all the tests, and even our customers or attendees can also bring their own materials, and we can test them during the course or after the course or before the course or whatever. So just to remember that we did our last training edition in June, and it was also a success, and well, we are thinking also to maintain it during the next year. Okay, so well, I think that we have finished with the questions, and now we have the coffee break, and we can be back in a little bit more than half an hour.
Okay, so see you soon and have a nice coffee break.
Okay. Hello, so we are back again in the workshop. So For the next presentation, we have with us Will, that he has to wake up really early in the morning. So yeah, so it's 4 o'clock. So
In the US, yes.
in the USA, more or less. Yeah, 4 o'clock.
Yeah, it's pretty early over here.
So well, sorry. We have Will Mars with us. Will, it's a very close collaborator of Lear Ticker. We have a long history of collaboration since almost 10 years ago, collaborating in the fatigue characterization and simulation area. And Will is the founder of Endurica, and Endurica has the first commercial software related with the fatigue simulation. And today he's going to present us overview of the different possibilities that this software is showing in the railway industry, and also take into account the multi-channel solution that they are offering to the market. So we'll just go on, and you have the...
All right, thank you for the introduction, Jose Javier and Naizetti. Let me share my screen here. And if somebody could just sort of let me know that it's visible. All right, thank you. All right. So yeah, what I want to present today is an overview of some capabilities that are fairly recent, and that's the ability to deal with road load signals, and for purposes of fatigue life prediction in rubber. There we go. Just a little bit about Endurica. This is year number 15, almost 16 years now since I started the company. We are 100% focused on the intersection of elastomers and durability and CAE. How do you calculate fatigue life for elastomeric materials? When I started, it was just me, and today we are 8 people. In that time, we've managed to have our solutions adopted by more than half of the top global rubber part suppliers. So anyhow, that's kind of the quick introduction to Endurica. Today, I want to talk through an example that we did for an automotive OEM, Ford. And it's the example of a before Ford accepts a rubber part from a supplier into one of their vehicle programs, there's a qualification step. And that qualification step involves, excuse me, being able to demonstrate that the part will endure the life of the car. And in order to specify the life of the car, Ford has recorded at the track or on the road 144 different types of typical events that a car has to live through. Those have been recorded at 1,000 hertz, and if you take all 144 history, it adds up to about 4 hours of data, which is about not quite 16 million time steps. In this case, the data are given as 3 loads, X, Y, and Z loads that are inputs to the motor mount. They're recorded in a data format called RPC, if you're familiar with that. And then these 144 events are scheduled together in what's known as a block cycle. So, they'll say, hey, this event number 1, during the life of a car, that event might happen a certain number of times, 100 times. Event number 2 might happen 1,000 times, and so on and so forth. So there's a schedule for these 144 events, and the goal is to show that the part can endure through that test schedule. Now, in the past, that qualification has been purely a physical requirement, but of course that's a high risk, high cost test to run, and so it'd be preferable if we could simulate the qualification test virtually. And to do that, what we want to do is we want to calculate how many repeats of this schedule can the part endure. And so that's what we're going to do in this example. And we'll be able to see kind of how the workflow goes. And also we'll be able to see a typical example of what the computational requirements are for doing this sort of thing. The image on the right is showing the mount in cross-section view, and all right, so that's the problem we're aiming at. In order to solve this problem, there's a couple different tools that we're going to use in the workflow. CL, DT, EIE, these are what we call our fatigue solvers. Each solver has capabilities that we'll use in different parts of the workflow. So the CL tool is, you could think of that as the core fatigue life calculation. So that's where we set up our material models, and it's kind of the core workflow. If you only use CL by itself, it's a post-process. CL by itself can do one use case. Of course, we have a schedule, which means we need to accrue damage incrementally, and that means that we're going to need the Endurica DT add-on to CL as well. The DT solver allows us to accrue damage across a schedule. It allows us to calculate residual life. If we want to take into account changes of material properties with time, we would use Endurica DT for that. The final tool that we're going to use is a tool called EIE. That's an acronym, and it stands for Efficient Interpolation Engine. You could think of EIE as really a method for managing the very large number of time steps that you have when you're working with track data, right? That those signals are so large that it's not realistic to try to directly model those in Abacus, but with EIE you can do that. You could think of EIE as a little bit like a I see a lot of people talking about machine learning these days, and the promise of that is to be able to accelerate calculations, and so EIE is something like that. You train your EIE model and build, we call it a map, and once it's trained, then you can very rapidly calculate strain history for a final model. So those are the basic tools. The model of the mount is shown in this image. We're using hyperelastic materials. There's contact defined here. We have about 150,000 elements in the model, 30,000 nodes, just to give you a sense of the scale of the problem. Here's a cutaway view. All of the green parts are the actual rubber. There's this mount is sort of enclosed within a metal can or a metal cylinder that we've just modeled here with rigid shell elements. But all the green parts and the cross section that's shown in gray here, that's the rubber. And here's another view with the external can or cylinder removed. There's two meshes. We've analyzed both the solids and the membranes. We paved the surface of the solid model with membrane elements because that helps us to derive more accurate stress strain states on the free surface of the mount. And so because we expect cracks to initiate on the free surface, we want to get accurate stresses and strains on that free surface as much as possible. I mentioned that we are modeling the nonlinear elastic behavior of the rubber. To do that, we're using a third order Ogden hyperelastic law. What you're looking at here are curves showing the simple planar and equibiaxial tension stress strain curves for that material, along with the strain energy density function definition, W, and along with the material parameters mu1, mu2, mu3, and the alpha1, alpha2, alpha3. So pretty, I would say this is pretty standard approach to modeling the types of materials here. It's by the way, it's a natural rubber. I should mention a filled natural rubber. Now, in addition to stress strain behavior, if we're going to do fatigue analysis, we need to specify the fatigue properties of the material. So what you're looking at in this slide is an example of the fatigue crack growth rate curve on the left. It's a plot of the crack growth rate as a function of the energy input, just like the Metraviv folks were talking about in the last talk. And on the right, you're seeing what's called a Hay diagram. The Hay diagram is an output from the simulation, but it basically shows the effect of mean strain and strain amplitude on fatigue life. So where you see blue, those are combinations of mean strain and strain amplitude where the life is very long. And where you see red, those are combinations where the life is very short. And so you could think of this as just a contour plot showing how fatigue life of let's say a tension strip depends on mean strain and strain amplitude. In order to define that plot, we would also need to define the crack precursor size. And in order to do that, we will use crack nucleation experiments. This is a plot of the engineering strain versus fatigue life. These experiments were made on simple tension strips. The triangle data points are showing the actual experimental results. The theoretical line, the green lines that are drawn through the data, those are actually predictions of the fatigue model. In order to, as you change the precursor size, those theoretical curves will shift to the right or to the left. And the way we identify the crack precursor size for the material is by choosing the precursor size that lines up the calculated curve from the crack growth rate law with the observed crack nucleation data. In this case, that gives us a crack precursor size of about 12 microns. Now, once we've defined the material behavior, then we, before you do a fatigue analysis, you ought to make sure that your finite element model is behaving reasonably. Ford gave us experimentally measured load deflection curves for the X, Y, and Z axes. And here we've overlaid the results of those experiments with the results of our simulation. The experiments are shown in blue, and the simulations are shown in orange. And it's not perfect, but it's certainly, I think, a quite reasonable agreement between the simulation and the experiment. Another thing that Ford gave us was the recordings of each of the 144 different events. And what you're looking at here are examples of 6 out of those 144 things. You can see that they're Some of them are, they vary in length. So some of them are, very short events, maybe a wheel impact. Some of them are longer events. But like I say, they're recorded at about 1,000 hertz, and they basically define the force X, Y, and Z force inputs to the mount as a function of time. And then in addition, they also gave us this Excel spreadsheet, which specifies the schedule on which these events are played, right? So this is the definition of one lifetime of the vehicle. They would say file 1 is repeated. Let's see, in this case, you can see that the first item is repeated 12,000 times. The second one is 30,000 times, and so on and so forth. So this list goes on for excuse me, it goes on for 144 different events. But so we have this schedule that we need to take account of as well. So that's what's given to us by the user. And at this point, we're ready to go ahead and start working the problem. To do that, the first tool we're going to use is a tool, as I mentioned, EIE, Efficient Interpolation Engine. And we're going to use EIE. There's really 4 major steps to doing that. The first step is to build what we call it a map. And basically what we're going to do is the map is a set of pre-computed finite element results that summarize how the part will, what the stress strain state is for the part over every possible point in the operating load space. So once you've set up that map, then you're ready to go ahead and do the interpolation. The next step is to bring in the load histories that you want to analyze. Again, those can be specified as CSV or RPC files. And then once you've set up your map and your histories, then we actually run the interpolation job by playing those histories into the map. And what we do is for every time step, we obtain the stresses and strains at that step by interpolating in the load space from the nearest neighbor load cases that have been included as part of the map definition. What's really nice about this procedure is that it does allow us to account for nonlinear behavior. That's important because rubber, is nonlinear in many ways. There's nonlinear material behavior. There is finite straining and kinematics. There is contact, and all of those different nonlinear effects can be represented using this mapped approach. And then finally, once we interpolate to get stress strain history, the final step is to solve for fatigue life. To do that, we would use either the CL or the DT solver, depending on the requirements for the analysis. In this case, we're going to use Endurica DT because we have a schedule of 144 events. All right. So a little bit more about this idea of a map. A map basically consists of a set of grid points. So I'm showing those here in gray as an example. This would be an example of a 2-dimensional map. So if I had 2 channels, X and Y, for example, and if I wanted to do 4 as a simple, a simple method for generating the map would be to, let's say, use a rectangular grid. There's many different approaches you can use to build the map, but just for the sake of argument here, let's think about a rectangular grid. And if I do 4 different load levels, in X and 4 different load levels in Y, then that means that I need to pre-calculate 16 different finite element solutions at each combination of X and Y in order to prepare my map for use for interpolation. Now, of course, when I start feeding my signal, my X and Y signal into the map, that's going to be the blue line. The points on the blue line, the signal points, those points are not necessarily going to fall exactly on the gray grid points. And so, I know the stresses and strains at the gray points. So in order to get the stresses and strains on the blue line, I'm going to need to interpolate using the, for each point, we'll use the nearest neighbor. So for this point here, we would interpolate from these points here. For this one here, we're going to interpolate from these points and so on. So as an example, here's a 3-channel signal. If we were to feed that into a bushing, you can see here the set of finite element solutions that we would pre-compute. You can see the deformed state of the bushing at each case. You can see that we know the full stress strain field at each of these points. And basically the process of populating this map is what we call map building. And like I say, after we've built the map, then we can play the road load signal into the map in order to get our interpolation. And once we've done that, we can run, in this case, we've run Endurica CL and CL, because in this case, there's just one signal. So we can run CL, and CL is going to tell us how many repeats of the signal, 36,000, does it take to, cause cracking in the part. It's going to tell us where the part fails, and so on. So in order to build the map, there's a few steps. The first step is to specify the map, the number of channels in the map. EIE will support as few as 1 channel and as many as 6 channels. So if you have 3 forces and 3 moments, or they could be displacements or rotations or moments, those can all be inputs for the map. And then you'd also specify the map type. And EIE supports different strategies for populating the map. The simplest one is this rectangular grid that I've shown, but there are other strategies that sometimes are more convenient that you can also use. Now, once you've specified the inputs and the map type, then you need to also specify we call them branches. Basically, in order to populate the map, you're going to need to trace a certain path in your finite element solution to collect all of the results that you need for the map. So there's a step of generating this path that can be done automatically by EIE, or if you want, you can specify your own user-defined path or branches. There might be one, there might be several branches depending on how you organize the problem. If you're trying to get everything done in one finite element job, you would have one branch. If you want to break it into several jobs, you can, break it into several branches. You might want to do that if you're going to run the map over, sometimes people want to run on 2 or 3 different machines simultaneously. And so that might be a reason to break the job into a few pieces. Once you've done that, then you go ahead and execute your finite element job and collect all of the stress strain solutions. And then finally, once those results databases are available, then we associate each finite element results database to its corresponding branch. And at that point, the map is defined and ready to go. So here's kind of the overall workflow. We're going to start with the full set of signals, and we're just going to look at how they fill up the operating load space. EIE is going to define our load paths in that space. And then we're going to feed those load paths into Abacus in this case. We also support ANSYS and MARC, but in this case we've used Abacus. And the next step then would be to execute those jobs. You can see here the mount running through all of the possible combinations in the map. At this point we have a map, so we can go ahead and run the interpolations for all 144 events. That's going to give us stress strain history at step 5. And then once we have stress strain history for all 144 events, we can feed that into Endurica DT. And for each event, we can accrue the appropriate number of repeats of each event to build up the entire schedule. And then finally, we can come out with the number of repeats of the schedule on the part and look at life and failure mode and so on. So here's again the plot you're looking at here is the commands that EIE tells. EIE is going to specify this as the command on the boundary condition for the model in order to build the map. This covers every combination of X, Y, and Z loading, and that's the animation you're seeing. This is usually the most computationally intensive part of the process. In this case, the map you're looking at took us about 57 hours of runtime on 11 CPUs. Now, one of the questions that we sometimes get is whether the interpolated strains are the same as what you would get if you were to do that computation directly. Now, obviously, you can't do this for the whole signal, but we did take a little snippet of the signal, and we ran the simulation just with a direct Abacus analysis to see if the interpolated strains are the same as the strains we would have gotten if we had run the simulation directly. And you can see the comparison is quite good. Right, there's two lines here, but they overlay each other quite well. The blue line is the interpolated line. The red line is the direct Abacus solution. On the right, you're seeing basically a zoom up of one portion of this signal, just so you can see better how well the signals agree. So long as your map is sufficiently discretized, you're going to find really good correlation of your strains. But of course, the interpolated strains get computed about 10,000 times faster than you would do in the direct finite element solution. So bottom line, this is the workflow costs for this particular problem. To define the map took about 1.5 minutes. To build the map took us about 57 hours of Abacus. To run the EIE strain history interpolation took us about 8 hours, running on 32 threads. That produced a file that was 3.2 terabytes. So when you run these problems, you're going to need a large amount of disk space. And then finally, to run the damage analysis, that job to process the 3 terabyte stress strain file took about a day, running in parallel on 7 threads with DT. So after all of that, for this particular part and this schedule, the life came out to be about 9 repeats. So this was maybe an over-engineered part, could have been light-weighted maybe, but it does pass the verification. And you can see here, so we had this was about 15 million time steps and 144 events, 150,000 elements. And if you add up all the run times, it's about 90 hours of execute time, wall clock. All right, so I will stop there. But this is an example that shows that these days, in the past, I think we've had to take shortcuts and make guesses. But these days, we're in a position really to fully compute the entire qualification schedule for a part. And I think that's an important capability. And I think the run times are in the realm of what we would need to do this in a production engineering context. So like I say, I'll stop there and if there's time, I'd be happy to take any questions.
Okay, so thanks, Will, for your presentation. And now we have time for questions. Remember that you can just write an email with your questions directly to the ICET's email that you can read in the screen.
Okay, so I'm checking the email for questions, and I think we have one, and it's asking about other kind of applications that you have studied with EAE besides the Ford motor mount application you have shown in the event.
Yeah, sure. So the example that I've just shown here, this was the biggest analysis that we've ever done. We did this one last summer. We've applied this to a number of parts, and we have a few customers who are using this. We've used this quite a bit on bushings and mounts. In fact, I would say we've probably run this now, I don't know, on at least 10 different mount types of problems. We have also, we just gave a paper at the Tire Society where we use this technique to model the loads on a tire under track loading. So we've done this for a tire. We've also done a transmission mount. So lots of applications. If you can get the road loads, you know, and we have done. This was a 3-channel example, but we've also done 6-channel examples. Yeah, good question. Thanks.
Another question. In that case, well, it's related with the time. I mean, you know that the customers always want to. They are always worried about the time. So, is there any limitation on the number of CPUs that the software can use?
Yeah, one of the reasons, you know, we've only been doing we've only been doing these road loads problems maybe for 2 years now. Before that, the code was not fast enough to really process these. But what's changed in the last few years is that we have introduced multi-threading to the Endurica code. And what that means is that the code for the last 2 years has had the ability to basically break the problem up and split it over however many CPUs are available on your compute system. So if you've got 6 cores on a laptop, or 32 cores on an engineering workstation, or 250 cores, 56 cores on a cluster, your job execution times can scale with the number of CPUs. To date, and we've done some benchmarking. We've done some benchmarking up to 128. 128 cores is the biggest that we've tested. We have shown that the code scales very linearly. As you start to get to very large numbers of cores, you do have to worry about bottlenecks in terms of you know, memory speed and disk speed. You can hit bottlenecks, but the problem does scale at least very well up to 128 cores. So that basically enables, you know, the rapid analysis of very large problems.
I think we don't have any more questions, but it has came to my mind a question as Endurica users. How do we know how many points to use in the map you have shown during the presentation? How can we define that, the number of points?
Yeah, that's so that's a matter of, let's say, engineering judgment. You know, on the low end, you need at least so for a 3-channel map, you would need a minimum of 4 solutions in the map. If you do that minimum, what you're going to get is a linear map. So if you define 4 solutions for a 3-dimensional map, you basically get a linear interpolation. Now, since these are nonlinear problems, you're going to have to discretize the space more finely than that. One way to estimate the number of points is to think of how many intervals you want to divide each space axis into. So in the 2-dimensional example we showed, we divided the axis into 4 intervals. And so if you have 2 channels, 4 intervals would mean 16 grid points. If you have 3 channels, 4 to the power of 3 would be, what is that, maybe 64 grid points, and so on. So now, when you the larger the number of channels you use, the larger number of grid points. And like I say, there's a little bit of an art to just making sure that you've adequately discretized your load space. At the end of the day, you're kind of always trying to balance efficiency with accuracy. So the more points you put in, the more accurate it gets. But the more points you have to build in your map. So like I say, it's a little bit of an art. What we normally do is we start with a course map, and we make some evaluation of the errors in that map by comparing a direct versus an interpolated solution. If we find the errors there are too great, then we add points to the map to further discretize. And if you do that, then you can come up with a map that's appropriately sized.
Okay, thank you. Thank you for the clarification, Will.
Okay, Will. So thanks for your answers and thanks for your presentation. Of course, if somebody in the audience wants to contact directly Will, you have also in the presentation the different contact ways. Okay, so now we go to the last presentation. In that case, the presentation it's going to come from Aiseti, who is with us today. Well, Aiseti, it's a researcher from Learticker on the sustainable transport area. She did the PhD with us and in collaboration with the Basque Country University. And before the thesis, she did the bachelor in physics and electronics, and also the master in new materials, also in the Basque University. She's during the last 8 years, she's dealing with elastomers and dynamic properties, and now she's going to make a presentation related to the prediction and the control of the shear stress generated during the injection molding of a TPD product. So, go on, it's your turn.
Okay, so first of all, good morning to everyone, and thank you, Jose Javier, for the kind introduction. So today I will present some results we are obtaining in a research project where we are analyzing how process conditions can induce different orientation, distribution, and stretching effects in the hard and soft phases that we have in TPE materials, because as I will talk later, the unique characteristic of TPE is their biphasic structure, these hard and soft phases that they have, and we are targeting mainly in the application of these methodologies for anti-vibration components, because as we'll talk also during the presentation, they are appearing new challenges related with the noise and vibration in the electric vehicles, okay? And of course, in this project, we are also researching how these solutions can be applied to tune at the end the final mechanical performance of TPE-based anti-vibration components. In this regard, how to tune, for example, their static stiffness, dynamic stiffness, and also their vibration dampening capability and the fatigue life of these components. So this is an outline of what I'm going to present today. Okay, first I will briefly introduce LEARticker and particularly the sustainable transport specialization area that we have in LEARticker. After this, I will talk about the main motivation of the project that I will present today, which is related with the new challenges that are appearing in elastomeric anti-vibration components in the electric vehicles, and how to advance the use of TPEs for this kind of components. I will present the main findings and results that we are obtaining in the project, and finally a small summary and some perspective. So as I said, LEARticker is a technological center. We are located in the Basque Country in the north of Spain, more or less 40 kilometers far from Bilbao, and we are specialized in polymers technology. And inside the polymers technology area, we have two specializations, which are the health and the sustainable transport specialization area. And in the case of the sustainable transport, we perform research and development activities in order to address the main challenges of the transport industry or market. And we do this by, on the one hand, the generation of knowledge, okay, generate knowledge and transfer all this knowledge that we generate to the potential customers and sectors related with the transport industry. We focused our activities mainly in the development of methodologies or solutions to reduce the time, the cost, and the risk that is involved in the development of advanced polymeric products and the workflows that are used for this. And last but not least, in development of strategies towards the digitalization that are in line, of course, with the specific characteristics of each of the polymeric products, okay? And why do we do this in this specialization area? So the main goal is to enhance the efficiency and the sustainability in the development of these advanced polymeric products for the transport industry. So in this slide, we summarize all the capabilities we have and which are our key technology or expertise in the sustainable transport specialization area. So as you can see in the slide, we can cover all the value chain related with the polymeric production, polymeric component design and production for the transport industry. So we can go from material design up to end of life of the component. We have capability to develop new materials, to perform new compounding and design new materials. We can even do product and process development strategies. We have capabilities for injection molding, compression molding, and also mold and component designs, specific designs depending on the material we select. Then we have different machines to assess and to characterize the thermomechanical performance of polymeric materials and also components made of these polymeric materials. And of course, we also have capability to predict or digitalize their static, dynamic, or impact behavior. And finally, we can also characterize and predict the durability or lifetime of these materials and components, mainly in our case focusing on the thermomechanical performance, so mainly fatigue and creep behavior. So in all this value change that we can cover, our key expertise or technologies are, on the one hand, in regard to the characterization of and processing of polymeric products. Mainly we focus on efficient material level characterization for modeling. So how to efficiently characterize materials to generate material cards or material models to simulate their behavior in the final component, and always considering the influence of the process in their microstructure and in their final thermomechanical properties. And we also work in the digital world, and in this case we work in the integrative digitalization strategies, so strategies that are aware of the process influence on the modeling or in the simulation. So we can cover material modeling, process simulation, structural simulation, and even product design, okay? And if we take a deeper look to the simulation capabilities, as I said, we can close the loop because we can even do process simulation up to a structural simulation, and always passing through the material modeling, so the generation of advanced material models specific for each kind of component or material we want to predict or simulate. So this way, as I said, we can close the loop and we can consider the effect of the geometry, the effect of the process, and the effect of the material selection on the final component design. So in the case of the, if we now jump to the main motivation of the topic that I will cover in the event, the main challenges, this topic, sorry, we have some issues.
You can just wait a moment, and I think we have to share the screen because Will and the other can see. And just a second.
Sorry, we have some issues now.
That's it.
I think.
That's it. Perfect. Okay.
I can see it now.
Yes.
I will.
Okay. We had some issues with sharing the screen with the speakers, so now I can continue. So I was talking about our main capabilities, integrative simulation, modeling, but now if we jump to the main motivation of the topic that I want to cover in this event, this is mainly related with the new challenges that are appearing in elastomeric materials. So as we all know, elastomers are widely employed in the automotive sector, and they represent a key material for the anti-vibration components. But traditionally, these are made of thermoset rubbers, not thermoplastic elastomer materials. But nowadays, they are appearing new requirements, mainly related with the electrical mobility, that are pushing the replacement of rubber to TPE, as also Pierre has mentioned in the presentation. So in terms of the noise and vibration dampening applications, on the one hand, as we do not have this internal combustion engine noise, now the noise and vibration requirements are changing. So probably the material selection may be also changed. But not only there are appearing issues related with the comfort, but also with the weight balance and weight distribution that we have in the car, because we are adding new components, for example, the battery, and we are removing old ones. So these components need to be redesigned, and redesigned considering sustainability impacts. Okay, impacts and sustainability issues related with the recyclability of the materials, new needs and legislations that are appearing. And in this regard, TPEs are very attractive materials because they are lightweight, they are recyclable, and we have high design flexibility. So they are appearing need drivers to introduce TPEs for these noise and vibration control applications. And there are appearing a huge number of opportunities for this kind of materials for vibration dampening. So, but what happens if we want to advance the use of TPEs in anti-vibration products? So in this case, we need to consider their unique feature, which is related with this biphasic structure. Okay, they have usually always two phases, a soft and a hard phase, and they also have a very non-linear properties. So in order to redesign a new component with TPEs, we need to consider the influence of the process in this biphasic structure, and we need to consider their very non-linear mechanical behavior in order to perform a design based on the final properties, to optimize the final properties that we will have in the component. So our approach, our strategic approach for an efficient and sustainable TPE-based product development is based on the development and scale-up of consistent integrative modeling and simulation methodologies for TPEs. And in line with this research line, we have, last year we started a project to investigate the effect of injection molding parameters and also geometric features on the shearing stresses that are generated during the injection molding, in this case of TPV products, thermoplastic vulcanized products, which are a specific family or material or TPEs, okay? Here you can see a summary, graphical abstract of some results we presented in a paper we published during this year. And in this work we showed that the process conditions induce different states of distribution in the elastomer and thermoplastic materials that we have in the TPVs, and that these processing parameters can be potentially used to tune the final properties of soft TPV-based products. Because as you can see, for example, here, we were able, by considering these process influences, we were able to reduce the permanent deformation, the plasticity that we can have in TPEs. So this is good to have better elastic performance properties in the anti-vibration components, and even we are able to somehow tune the dynamic characteristics or vibration damping characteristics of the final component. So that means that addressing the effect that we have in the injection molding parameters on the shearing stresses that are generated during the injection molding represents a key aspect to design optimal TPV products. So following this research line, this year we have started a project to analyze this, how the shear stresses can be controlled and can be linked to the final properties of the TPV components. And for this, we are analyzing the use of Moldex 3D to perform simulations and to capture the shear rate that a TPV can produce, the injection molding can produce in a TPV component. So in this case, we are using a TPV, PPE-PDM TPV that was supplied by Celanese. It has a short A60, which is the range of hardness that we have in anti-vibration components that are used in the automotive sector. And in this case, we analyzed the different processing parameters. For example, on the one hand, filling speed, mold temperature, material temperatures. So parameters that we can check and control during the injection molding, but not only process parameters. We are also analyzing geometrical parameters. Why? because the redesign of a component, so shifting from rubber to TPEs, has other challenges, for example, related with the wall thickness, because in this case we are injection molding, so usually we need wall thickness less than 4 millimeters to avoid warpage, to avoid void generation, and also we want locally to analyze the effect of the injection molding on the shear rate, so that's why we also analyzed the distance from the gate, so we analyzed the generation of the shear rates in different positions of the plate. So we did in total 64 simulations of the TPB mold filling process, and as an output we analyzed how all these process parameters affect the shear rate in the different positions and for different plates with different thicknesses from 1 up to 4 millimeters. So once we did these simulations, we performed a full factorial design of experiments to analyze how the different process influences may influence the shear rate, and at the end, as we showed in a previous slide, the microstructure and the final properties that we can have. So these are the values analyzed. So we analyze different filling times, different speeds, fast and slow injection molding, different material temperatures, mold thickness, as I said, from 1 to 4, different distances from the gate, and we also analyze the thickness of the gate, so a more restrictive or non-restrictive gate. So as you can see in the histograms, we can see on the one hand that the mold temperature and material temperature have an insignificant effect. So these two variables have no many influence on the shear rate that is generated in the injection molding of these TPBs with different thicknesses. And it was interesting also to observe, if we compare the graphs, the curves, that the 1 millimeter case deviates a bit from the rest. So in the case of 2, 3, and 4 millimeter, the shear rate effect is similar, but in the case of the 1 millimeter, the influence of the parameters on the shear rate deviates a bit from the rest. And in terms of the filling time, we can also observe that a lower filling time, with a lower filling time, we achieve higher shear rates, okay? So this was a first approximation to the effects, but in order to go more in deep to the effects that we can have between, and the correlations we can have between process variables and shear rates, we also analyzed the linear correlation heat map, or the Spearman's correlation that we can have, in this case, to see how the process parameters can influence the shear rate at the different positions. So this is important because at the end, in a component, we want to analyze how locally the different process parameters may induce the shear rate in order to better optimize the geometry, the design locally. So here what we can see is that if we are in the gate, then the entry is the one that is affecting more. So having a more restrictive or non-restrictive entry affects the shear rate on the gate, but not in the other positions of the plate. But the filling time, yes, okay? The filling time has an influence on the shear rate in all the plate, not only in the gate, but also in the consecutive positions at the end or in the center of the plate, okay? Then here we can also observe how the thickness in the case of has influence, but mainly not in the entry, but in the other positions. So as I said, considering this, what we thought was, okay, so if we have these correlations between process parameters and the shear rates, are we able to generate a model, a comprehensive model to predict which is going to be the shear rate in different positions of the plate, because as I said, we want to have an idea locally which are the effects on the shear rate. So we analyzed if we are able, by knowing the shear rate at an exact position, at one position, if we are able to predict the shear rate in the other positions. So if we analyze the relation between the location 0, which is the gate, in the gate, and the other positions, it can be seen that there is no any relation between them. But if we exclude this, the 0 position, the position in the gate, then it was interesting to observe that we are able to predict what's happening in the other positions. That's it. If we know the shear rate at 30, there is a linear correlation between the effects in the shear rate at 105, and the same happens with the other ones. Okay, you would say me, but here you have some points that are not well correlated. So these ones are the ones related with the 1 millimeter case, but as I previously also discussed, the 1 millimeter case is the one that deviates a bit from the rest, and if we exclude this, the 1 millimeter, and we only use the 2, 3, and 4, in this case, we get a very good correlation and linear correlation between the shear rates at the different positions. So this is very interesting, as I said, because we are able to correlate the process parameters with the shear rate, and we can simulate this or predict this by only knowing or only simulating one point, not performing as we have done 64 simulations, but less simulations in only one point of the plate. So as a summary, we can see that previous studies that we have done have revealed that the imposition of the different shear rates or shear stresses during the injection molding can induce a non-isotropic characteristics in PP-EPDM TPBs. So that's why predicting the impact of these injection molding parameters on the shear stresses that are generated during this injection molding emerged as a pivotal factor in designing TPB products that are optimized for anti-vibration performance and optimized for the new requirements that are appearing in the electric vehicles. And in the case of the project, we saw that among the analyzed variables, the highest correlation was with the filling time. And it was interesting, as I said, to observe that if the shear rate at a specific position other than the gate is known, a strong linear correlation exists with the other positions at plate level, which, as I said, allows the prediction of the shear rate at the remaining positions. So we can have a full overview of the effect of the processing on the shear rate in different locations of the plate. And as an ongoing activity, as I said, during this project, we have been linking how the process parameters affects the shear stress and the microstructure evolution. And now we are working on how all this affects the mechanical performance. So we are doing in these plates that have been injection molding, we are doing different quasi-static, dynamic, mechanical analysis trials to, at the end, link the process parameters with the mechanical performance, and, as I said, to do a properties-driven process and component optimization, okay, to be able to tune finally the key parameters that govern the performance of anti-vibration components based on TPE materials. So that was all. I would like to thank you all for your attention, and if you have any question during the event or after, you can just contact me by sending an email to the email you can see in the slide. So thank you.
Okay, thanks, Aiseti, for your presentation. Well, we have a couple of questions. The first one is related with the material that you have used in the studies. It's a TPV Shore 60, and the question is, are you expecting similar results with other harnesses?
Okay, that's a good question, and that is something we analyzed in a previous work, and something that appears in the publication that you can show here in the screen. So what we observed is that the anisotropic characteristics or the process influence increases with decreasing the hardness level. So in this research project, we analyzed different TPV grades. They were all from Celanese, so they were PP, EPDM TPVs with different hardness, so a Shore A60, Shore A87 and Shore D41. And as you can see there, the main influence or tunability was for the Shore A60. Okay, so if we move to softer materials, we will have more influence on the process and anisotropic character, which is interesting because in antivibration products, this is the range of the hardness that we employ. So that means that we will be able to tune if we are able to advance on this kind of strategies.
Okay, thanks. Of course, we'll raise Pierre. If you have also any question, you can just go ahead. Well, another question, that's an easy question. Which is the software that you're using for the injection molding simulation?
Oh, okay, so in this case it's Moldex 3D. Okay, so we are using this because it's, as I said, a software that on the one hand they have a lot of materials available, and so we can use the data that is available there about the viscosity and influence in the melt rheology. And on the other hand, because it gives us this key parameter, which is the shear rate, and even in the different positions during the thickness. So Moldex 3D is the software we are using for it.
Okay, thanks. Okay, so any other questions from the other speakers?
I've got a question.
Yeah, great.
Sure.
So this is Will. So my question is so for this particular material, is there a dependence of the material properties of the final plaque? Is there a dependence of the mold temperature on for those properties? And have you looked into that at all?
In this case, we have analyzed the effect of the mold temperature, always considering the recommendations of material supplier. Okay, so the supplier recommends not to exceed 70, so 30-70 are the limits. So we analyzed what happens if we injection mold with a mold temperature of 30 degrees or 70 degrees. And what we observed is that the material and mold temperature have few effect on the shear rate. Okay, so it seems that they are not the main or key parameters to control if we want to tune the final properties of these materials. Of course, as I said, now we are validating this information that Moldex is giving in terms of the shear rate with the mechanical performance, because we want to double check and we also want to control if even the shear rate has no many, the mold temperature has no many influence on the shear rate, what happens with the mechanical performance. So once we do this, we will see if, as a conclusion, we can say no, it has no any influence, or it has some influence on the quasi-static, dynamic, or fatigue behavior of these materials.
Cool, thanks.
Okay, so I think that we can start finishing the workshop. Of course, yeah, I would like to thank all the speakers, Pierre, Brice, Will, and Iseti for the nice and deep presentations. Yeah, Will? No, okay. And well, just to summarize a little bit the workshop, I think we have been getting a lot of information about the different uses of TPE material in the automotive sectors, and also Pierre has give very clear points related to the sustainability and which are the things that are accepted in Renault from the Renault point of view, and which are the ones that are not accepted. And it was very clear for us. Brice was giving a nice overview of the capabilities of the DMM characterization technologies, and also the wide branch of machines that they are offering to the market. Will always a very deep presentation about how we can use simulation techniques in order to predict the long-term behavior of the different elastomers. And Iseti was giving some points related with the importance of the process parameters when we are working with thermoplastic elastomers, and how important it is to have a clear understanding of which is the effect of these parameters in the final properties of the part. So well, again, thanks to the audience also to attend for attending this workshop, and you will have news about news from us related with the next events, and we can start also preparing the DYNAeLAST event for the next year. So thanks a lot. Thanks, Iseti, and I hope to see you soon.
Thank you.
Thanks. Bye.
Thanks,
Thank
guys.
you very much.
Thank
Bye-bye.
you.
Thank you. Bye-bye.
Bye, guys.
Keep in touch. Bye-bye.